Hello guys, welcome to 365. So today we are going to go over a new topic called a new machine learning algorithm called KNN. Okay, so today will be kind of an introduction to the first of the algorithms that we're going to discuss in the class. So basically that's the plan. Also, I believe you have a homework assignment that I posted. I don't know if you had an opportunity to take a look at that homework assignment, but it is posted on Blackboards or Brightspace. So let me actually screen share just to kind of point that out in case you haven't seen it yet. All right. Let's go to content, and then let's go here, table of contents. All right, and you can see under the machine learning pipeline and feature engineering, you can see that I've already, thanks to Ryan Frederick, I was able to add the PDF here, right, that we discussed in class, so you can have that for your own reference. And also I've added the homework assignment, so you can take a look at that. There should be a file in here, right? And you can see the problems. Let me see. Yeah. So basically, for the following 5 classification problems, identify and or define the following. So there's 5 problems, and you need to identify, what is the X matrix, the Y vector, what are the samples, the classes, define a set of features, define the dimensions of X and Y, and indicate what they mean. Okay, so the idea is that you're gonna kind of, describe all of this in your homework, and you're gonna do this for 5 problems. So imagine you're building a classification model for a network intrusion detection system, right? And then imagine you're building a classification model for a speech-based classification model for a telephone menu, right? So if we're all familiar with the, for English, press 1, and then, it gives you those options. So think of that problem. Number 3, a classification model for movie recommendations, such as what Netflix does. Number 4, a classification model for weather monitoring, right? So this would be, would have some sensors, and then, you monitor the weather. And then number 5, a classification model for cancer diagnosis using 3D image scans. Okay, so these are basically the 5 problems, and I really just want you to identify these elements. So this is just, requires a little bit of thinking, and then you will submit your homework assignment. So are there any questions about this assignment? Are there any questions? Guys? No questions? All clear?
No questions.
Okay, great. All right, yeah, so that homework, I think it's open until Sunday. Double check. I think I made it due like Friday, but it's really, I think it'll stay open until Sunday. So let me know if you have any questions, and then hopefully once everyone submits, we're going to discuss it and just try to, see what answers we got. Okay, so let me close this. Oops. All right. So now let me go back to content. So as you know, we've talked about the machine learning pipeline. Let me go here. Right, we've talked about the machine learning pipeline last week. Today we're going to focus on one of the elements. So if I go, let's say, to our website, right, and let me share that. Okay, you can see it. All right, so basically, if you remember, I created this pipeline of machine learning in general, right? And you guys are currently, for your homework, you'll be working on some parts here, right? So identifying the problem and then arriving at the X and Y over here. And then, as you know, after that, we just have the machine learning algorithms, the ML algorithms. So there are many depending on the type of problem that we are looking at. In this case today, we're going to discuss the most basic machine learning algorithm, right? So I'm not really getting into getting a data set and analyzing the data set yet, okay? Instead, we'll get to that at some point where we can feed a data set and then run through the whole, and then, until we get to the performance metrics. So we'll complete that pipeline when it's appropriate. But for now, I really want us actually to focus on just the algorithms, right? So get a feel for a lot of these algorithms. And I think, KNN is really a great algorithm to start with because it's the most intuitive, I think. And so we'll take a look at that. And then from there, it starts to give you ideas of how the more complex algorithms might work, okay? So that's really the plan. So as you can see here, KNN, which stands for the K nearest neighbor algorithm, we will be starting with this one today, okay? So we'll get into the algorithm and you will have a homework assignment about KNN. Basically, I'm gonna ask you to implement KNN in Python, okay, from scratch. Now, I'll help you out, of course, but that's really the goal that I want. For some of these algorithms, I want you to implement little parts of them. Obviously, as the algorithms get more complicated, we will only possibly implement parts of them to kind of understand how they work. And then just be aware once we move into the more solving problems, et cetera, we start using libraries. So we don't have to code the algorithms from scratch every time. But as this is a foundations class, we want to do that to give that foundation, basically. All right, so let me get the slides. I have some slides for this. So let me just open them. All right, so I'm going to go ahead and share the screen. Okay. So now let's go ahead and share. So you should now be seeing the slides. I will be posting these slides over to, once the lecture is over today, I will post these to Brightspace so that you can have them for your own reference. Okay. All right, so let's go ahead and start the slideshow. Okay, so today, as I said, I really like, to jump into the algorithm KNN. I'll explain how the algorithm works. And then just keep in mind that what you want to do is you want to be able to implement it. And this will be great because to implement KNN, you will need to have some data, right? So you are basically, you're gonna need some data, and that will also cover the whole pipeline as we try to make all of this work. All right, so the algorithm, this is a machine learning algorithm. Right, it's called a K nearest neighbor. The K stands for, it's a number. So the K, the letter K is a number. And usually it's an uneven number, right? So 3 or 5, not really more than that. So it's usually either 3 or 5. And you'll see, it's an important parameter because this algorithm is about comparing a test sample against all the other samples in the train set, right? So that's really basically the idea. So a KNN algorithm works where you have, let's imagine all these different points, and then you get a new point, the square. Well, now you start calculating distances, right? Distances between the original square and all the other points in the space, right? So obviously this brings up a lot of things. This brings up geometry, right? So it brings up geometry a little bit, and things that you learned about before, and so we're gonna think in terms of geometry, and that makes KNN, you know, an algorithm that's easy to understand because it's very physical, right? You're thinking of a very real thing, right? So now, basically what the K does is that as you compare the distance between this sample and all the other samples, you basically get those values, right? And then you sort them in ascending order. So you go from the shortest distance to the longest distance. All right, and then once you've selected then you select, let's say, the 3 shortest distances or the 3 closest samples or the 5 closest, and then you kind of take from that, you evaluate, well, what type of samples are these? And that's really, in a sense, the algorithm. But that brings up a lot of important elements that we need to address, okay, that we need to address. So the learning objectives here, the student will learn about KNN, right? KNN is a traditional machine learning algorithm. So what that means is like one of the more basic algorithms that have existed for a long time. As I said, it's very simple to understand. It's a simple algorithm, simple mechanism. You know, if you ever fall into a black hole and end up in the other side of the galaxy with no technology, right? You can still build a KNN, right, from scratch because you will understand how the algorithm works, and it's actually pretty intuitive. Okay. So, so KNN is great for, you know, for academic purposes. Obviously, it can be used for real applications. However, it does have some limitations, right? So KNN is not necessarily for big data, although parts of it can be made in parallel, right? So you can compare one sample to multiple batches of samples, right? So you can therefore parallelize the algorithm, at least in parts, and that allows you to speed up the algorithm. But the problem is this is one of those algorithms where you don't train your model on the data and then create a model of it. Here, you actually, the model is the entire data set. So you usually end up looking at, you know, all the data for it. But it's great for quickly prototyping your data set, and KNN can actually do, you know, really well. Okay, so it's part of, you know, when you hear me talk about like traditional algorithms versus big data algorithms, you know, the distinction would be, as you see here, traditional will be, you know, KNN, naive Bayes, decision trees, just the more basic types of algorithms, whereas big data will be the newer, you know, neural networks and deep learning in particular, right? So deep learning, you know, the frameworks that we can use for deep learning have been optimized for big data, whereas KNN, you know, is more of a traditional algorithm, but it can still, I mean, with today's computers, even, you know, a good laptop could handle for KNN in a feasible manner, I would say easily a matrix that is 100,000 samples by, let's say, 5,000 features or 5,000 columns. So I think, you know, it's still pretty good for most of the data sets that we could use in the class, and even for some applications as well, some real applications. Oh, you can see here, you know, so for instance, this is an example of a matrix that could be handled by KNN, so 10,000 rows. I would say even 100,000 rows, so 100,000, and then yeah, 10,000 columns. So that type of a matrix would be fine, I think. Obviously, when we're talking about big data, you know, that, you know, you mean more than, you know, so more than 1 million rows or samples, 10,000 columns or so. So we're talking about, you know, much bigger things. Okay, so just keep that in mind. KNN, therefore, will be a type of a traditional machine learning algorithm. Okay. Now, one of the key things that KNN brings up is this idea of the vector space model. All right, so basically here, this is a very physical thing with KNN, that we need to think about, right? So in KNN, so imagine that you're in a room, right? So imagine that you're in a room, right? So you're in a room. You're in a room, there's, a door, right? And then people come into the room and, there's a chair, right? There's a chair, and then there's, another chair, right? And then there's a, like a table or something, right? So the idea here is you bring in, another object. Let's say just a circle, right? So the question, or let's say actually a star. So now the question is, what item is it closest to? Well, you look at the items in the space. So it's going to be, this is a distance there, that's the distance, and this is the distance. So obviously, the star is closest to this chair, the first chair, right? That's the one that it's closest to, and it's furthest away from another chair. So that's what we're doing with KNN, basically. That's really what we do. So we first need to define a space, right? So we define a space, right? Which is defining the vector space model. And that's what we're going to talk about in a second, how that can be done. And then after that, once you've defined the space, the next thing is you just need to define a metric of calculating distances. So we learned the, so we learned the Pythagoras, right? So Pythagoras' algorithm, right? Where we learn how to calculate the distance, the sides of a triangle. So if you remember that equation, that's basically the basic distance that we can look at in a space like this, right? So we know something about how, if I remember correctly, we have a square, b square. You guys remember that? And so there's a relationship here, right? That I believe says something like a square plus b square. And then this becomes, if this is root, right? This becomes a square plus b square, right? So that's the equation that we know, Pythagoras. And that basic idea allows us to determine this distance, right? The distance of that triangle. And another way of putting it is, if we put that triangle into space, now we can calculate the distance between this point and that point. So really, all we have to do is we have to identify the coordinates of those points in the space, and then we have a notion of calculating distance. And that's exactly what we're going to do with KNN. So we need to use an equation, right? Now this equation that I drew is basically for, something, a small space, right? So we can extend it to have more parameters when we have spaces that are, larger, right? That are larger. So we'll see that in a second. But in essence, that's the idea, okay? That's the idea, that we need to define a space. And that's why you see that we have here this, three-dimensional. So in this case, this is 3D, right? And the space, as you can see, is defined by X, Y, and Z, which, by the way, are also the features F1, F2, and F3. So really, whenever you set a data set, right, and that's why when we talk about those X matrices, when we have X is a matrix of n by m, right, where n are the rows and m are the columns. So basically, this m corresponds to the number of features that you have here. So this is a space of 3. Therefore, m is equal to 3. And so we will see in a second how a data set actually is a representation of a vector space, just of, depending on how many features you have, m, then that determines how many that determines how many axes you have here, right, in this vector space. All right. So let's so that's the general idea. We'll come back to this. The vector space model is actually pretty important as a concept, right? And it's basically every time that you create a data set, you know, so that's why the homework that you're doing that I assign is very important, because really whenever you define this X, right? Whenever you do that, you define that X, you are technically defining a vector space, okay? That kind of looks like this. And then by defining a vector space, you now have this property of geometry. And within that geometry, you can apply things like the Euclidean distance, right? So you can calculate these kinds of distance metrics. Are there any questions about this slide, guys?
No.
That make sense?
Yeah.
Okay. All right. So this is the idea, right? So now so hopefully that helps us as we move into the algorithm of KNN itself. Okay, so let's go ahead and do that. All right, so let's think of a problem of, for instance, for KNN, right? So we want to build an intrusion detection system, some kind of a classifier, an IDS. Okay, so basically we have data. We have binary data, right? You know, we have binary data, email, you know, YouTube, whatever it is, and we're going to call email, web traffic, YouTube, goodware. Okay, and then we have you know, bad data, you know, network attacks, for instance, right? So you have denial of service attack, malware, spoofing, etc. So we have really two categories or two classes. So KNN is a supervised learning algorithm, and that basically means that because of that, additionally to the X matrix, KNN needs the Y vector, right? Remember that the X holds the data, you know, the data about the features for each sample, whereas the Y vector holds the label of each sample. So we talked about this last week. So now we're going to assume that the samples in our problem, for instance, here are going to be packets, right? Network packets. And we're just looking at each network packet. We extract the features from the headers of the packet, you know, the IP header, TCP header, etc. And then we know we've labeled some of these to be regular goodware, you know, people just multimedia, YouTube, web, email. And the other ones are, on another day, you were able to capture some network attacks like denial of service, malware, spoofing. And so those have been labeled as badware. So basically we can use labels like -1 and +1, or we could do 0 and 1, etc. Right? So we can use different labels. So if we think about that problem of an IDS and an intrusion detection system, then we can take, you know, an initial packet, right? And now each packet needs to be represented as a vector in this vector space, okay? The vector space, you know, if we have, you know, we have a space of one line, one axis, two axes here. Remember, these axes are always going to be, you know, what is called orthogonal, which basically intuitively means they need to be 90 degrees from each other. Because when they're 90 degrees from each other, they're independent, right? And that's the key thing. They're totally independent, hopefully. If you have 3D, obviously, that, you know, that's kind of like racing a new arrow facing you, but which we can draw like this. And we know also that this, you know, is kind of 90 degrees to that and to the other axis as well. And then these spaces, although we have 1, 2, 3, mathematically, we can add more spaces, right? More spaces. And just, although we can't visualize them, we just should know that these spaces, every new axis that we add has the property that it'll be 90 degrees to the other ones. They're all 90 degrees. They all meet that property of independence. And that just holds mathematically, so we don't even have to worry about it at all. Okay? So now so when we have that concept then, all we need to do now is figure out, which is kind of the homework that you're doing, right? You need to figure out how to convert the packets into the vector space model, right? Convert the packets into the vector space model. Find X, define Y, and then once we have them, we're going to implement for our model the KNN algorithm, right? And then the KNN algorithm, when we apply it to a test set, of the same, of different samples, but with the same features, it's going to then, predict, I think it's normal traffic, or I think it's bad traffic. So either good wear or bad wear, basically. So that's really the idea, okay? So here, for instance, let's think of, we take the packets. So we take the network packets, and each packet is going to be a sample. So PKT1, PKT2, PKT3, right? So each packet is a sample, sample 1. So that's the number of rows. So we can have, let's say, 100,000 packets. We can always get a lot of packets, right? So we take a packet, and then we need to define the features, right? So we're going to do dot, 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 fn, right? The features are the thing that I'll leave that for you guys to figure out in your homework, but it's going to be information from the packet, like, number of packets sent, or sorry, number of bytes sent. A packet can have that type of information. Number of packets sent, number of packets received, protocol, etc., right? Different values, hash value or checksum, size of the, something. So this is feature engineering, and I'll just leave that to you guys to figure out for the homework. But let's just imagine there are 20 features that we define. And we have 20 features, and we have their bytes sent and bytes received. Bytes sent is F2. So F2 will be bytes sent, and F3 is bytes received. And Fn and so on, dot, dot, dot. So we can define 20 features for this. Remember, F2 is that column, F3 is that column. Every sample needs to have that column and a value. All right, so this is going to be 100,000. Okay, and so we're going to have a value associated with F2 for each sample and a value associated with F3 for every sample. If you think about it, F2 now becomes, in the vector space model, an axis, F2. Then F3 becomes another axis, right? F1 is another one. F4 is another one, and they're all perpendicular, right? Or orthogonal, as the correct term is. And in that sense, we end up here with a space, because we have 20 features, that is R20, a space of size 20. However, we usually, just for academic type of understanding, we're always, because we can't picture things in higher dimensional spaces, we are just going to think in terms of, let's say 3. So 3-dimensional, or maybe 2-dimensional. That usually allows us to get the intuition, and then we just have to know, oh yeah, by the way, this generalizes to higher dimensional space, because the math holds, okay? The equations will work if we expand them to higher dimensions, even though we can't really visualize it physically. Okay, so That's basically the idea, and that's what a vector space is. So really, whenever you have this matrix here, right, you have technically a vector space. So whenever you're holding an X matrix, remember this is X, right? The X is the vector space. The labels, the Y vector, are not the vector space. Instead, what they are is the following. Let's say that I have, you know, this sample, that sample, that sample, and then I have this sample, that sample, that sample, that sample. You see that? So that just means that some of these samples are zeros, some of these samples are ones, right? So they basically represent these two things. So what the label does is imagine like for each sample, I can change what it is. So now these on this side are squares. And that represents a 1. So a square is a 1. And then over here, these are circles, or actually, let me do stars, stars, stars. Okay, so stars are 0. Okay, so stars are 0. So basically, that's what the labels imply. In the vector space, it's kind of like based on the label, that's the color that we're going to paint them. You know, red or blue, but they don't represent the vector space itself. Another intuition about this is that, let's say that we have the following. So we have, we're just going to take F2 and F3 to keep things simple. So another intuition for this F2, F3 is that, you know, F2, because we've normalized the data, the values really just go from 0 to 1, let's say, right? They go from 0 to 1. So here, it's going to be 0.5, 0.8. Whereas for S2, it's going to be 0.1, 0.2, right? Just some values that I picked. So how does that translate? F2 is the whole axis from 0 to 1, and F2 is the whole from 0 to 1. Right? So basically what I would say is if I want to plot S1 in this space, I'm going to say, okay, S1 is, so S1 is 0.5, right? 0.5 over here and 0.8. So it comes out to about there. That's S1, right? And I've managed to plot it. Okay, so that's the way to think about it. If I want to plot S2, the next one, then it's going to be on the F2 axis, it's about 0.1, so somewhere around here. And then on the F3 axis is 0.2, so probably around there. So then the point comes out to here, and that's S2. You see, so that's the basic intuition. The columns become these axes, and then on them you can plot, you can use these values here to plot your points. So basically, every sample is a point. All right, so as you saw, S1 just becomes a point, S2 becomes a point, S3 becomes a point, and then you start to create this vector space of values, right? And as I said, if we were just using 2 features, then it's R2, just 2. If we add a third feature, we have 3 dimensions, but this can be extended to 20 dimensions, 1,000 dimensions. It really doesn't matter because it's really the same math. We just have to change the equation a little bit and everything else will hold. Are there any questions about this, guys, what I just said?
No questions.
Right, so if you're understanding this part, that's great, because this is really the hardest concept maybe to grasp. And then after that, you know, the algorithm is really just figuring out the code, which shouldn't be too bad. And I'll give you, enough time for that. But that's really, what we're going to do today. Now that we have this intuition. Okay, so now that we have this intuition, we can take a look at the slide. And we can see we have our X over here. So I'll just write it right here. Have our Y. As you know, the Y's are the labels. X samples and the features. Okay, and then remember, the features are coming from the packet itself, right? So we're going to look at, remember, a packet can be divided into an Ethernet header an IP header. For TCP, it's using a TCP header, which might include a payload, right? And so this is the information you're going to extract. You know, you would use something like Wireshark or the libcab library from C++ or Scapy or something like that. And then you can extract the different values, okay? Extract the different values. So you know an IP has a protocol, has a source IP, destination IP. TCP has source port, destination port, packet sent, packet received. So all of those, for every packet, you would populate these columns, right, based on, you know, the corresponding value that it has, okay? And so that's what you do, and then you end up with your data.
Excuse me, Professor Calix. Something's wrong with your mic. I think it's coming off kind of robotic.
Robotic?
Oh, it just fixed itself.
Yeah, it's better now.
It's better now?
Yeah, that's weird.
Did it last a long time?
Like 2-3 minutes.
Yeah, sometimes when that happens, I just like reset the volume on my microphone. But you're saying now it's perfectly fine.
It actually just kicked in a little bit just now, but I mean, it's terrible.
The thing that I know to do is, give me a second. How does it sound now?
Perfect.
Perfect. Okay, yeah. So when that happens, just let me know. Usually, I just adjust the volume a little and it fixes it. Okay.
Okay.
Yeah. Please let me know if it.
All right. Thank you.
Okay. Let's see. I need to share. I think. All right. So I'm sharing now. Hopefully, you're seeing the slides. Slideshow. Okay. So we were here in the. So we talked about the vector space model, and this is really, as I said, a very important topic, right? Although I'm actually focused on KNN. KNN is pretty visual, pretty geometric, and so it's pretty good for grasping the vector space model, I think. So let's go ahead now and move on to the next one, right? So as I was talking about, the idea of the data set is that the samples do not affect the dimensions, okay? The samples do not affect the dimensions. What affects the dimensions is the size of X. So we have here, let's say M by N, and then, you know, this would be then M by 1, right? So M does not correspond to the size, but it is N that corresponds to the size of the vector space. So this, for instance, so the generic form will be Rn, right? Rn, and that's really all you need to worry about. Doesn't matter how many samples. That just means, you know, I have a dot, dot, dot. Remember, you can have an infinite amount of dots in here, right? So that's not a problem. And then just, you know, just for completion here, this space is R2. This space is R3. This one would be 1, 2, 3, 4, 5, 6. So this is R6. Okay, so these are all the spaces that you have there available. Okay, so now that's basically the intuition. So N is what determines the size of the vector space. Okay, so now we can more, you know, we can more explicitly think about this. You know, I have a protocol, right? The protocol that's in the IP header. Is this a TCP packet, UDP packet, ICMP packet? So that's the number that's going to be in there. Destination port, source port. These could also be, we know that ports go from 1 to 65,000, right? So any value in between. Now, I usually get some Some people don't like this example. I like to use it because destination port and source port are things that we all understand. We remember it's one from 65,000. But the problem is that, and that's why I want to stress this. This is supposed to be a scale, right? And the point is that there is meaning in the fact that something goes from 0 to 1 if it's scaled, or from 0 to 10,000, let's say. Okay, so let's say something that we all understand, right? Like age. So from 0 to 100, we understand. This is younger, getting older, in that direction, right? We understand that. However, when I use the example of, let's say, the source port, I'm implying there that I go from 0 to 65,000, right? And what do we know about port numbers? We know that port numbers 22, right? We know port numbers 22, port 80, 443. And then we know that, usually ports like 50,000 could be source ports, right? Not necessarily destination ports, but they could be source ports. The problem with using this like that is that 443 is not necessarily, there is no concept of somehow 443 being greater than 80. Do you guys see that? In source and port numbers, 443, yeah, it is greater in terms of numbers, but the meaning of the port 443 is not somehow greater than the meaning of 80. It just means that 80 is web, 443 is HTTPS, right? So I think, or database. So there's a categorical meaning, but not a numeric meaning of like age or weight or something, or income or something like that. Do you guys understand the difference there?
Yep.
Yeah.
So that's very important because I usually keep this slide to make this assertion, but really we wouldn't use source port destination protocol. We would use something more intuitive of increments of numeric values, for instance, bytes sent. Right? There we do have a meaning of, let's say, I don't know, that 100,000 bytes are sent, right? So we have that meaning of we send from 0 to 100,000 bytes, right? And on the other end here, then, we would say bytes received right? And then that would go also, let's say, actually this one, for whatever reason, you always receive less than you send. Let's just say that. And that's just going to be 50,000. So then it's still, 40,000 is greater than 20,000. You did receive more bytes. So that holds for this type of problem. Now, if you notice, there's a bit of an issue there also that I introduced, and it's the fact that really, if I represented this properly, this would go from 0 to 100,000. Let's make this actually simpler by saying this is 10,000. So now this one actually is shorter. Do you guys see that? It's not as long as the, it's 1/10 basically the distance. This is a problem in machine learning. Okay, this is a problem in machine learning. And this is why I keep saying you have to scale the data. Okay, whenever you hear me saying you got to scale the data, because when you scale the data, all values in here are proportional to this scale. And all values in here are proportional to that scale. So you can just create the same scale for all features, and then the values will be proportional within those scales, but actually they'll be more meaningful because this scaled will just be equal, two axes of equal size from 0 to 1. And now the values are just plotted. So whereas they were kind of bunched up here, now they're a little bit more scattered in size. And then here also, so they're more proportional. And that's what scaling is about. Machine learning algorithms do way better when the data is scaled. When the data is not scaled, you have problems because here you may not see it. But I could imagine another example, let's say going back to protocol, where I have bytes sent and it goes from 0 to 100,000, and then protocol. And look at how tiny that access would be. So basically, you wouldn't really notice the difference, right? Because everything would be bunched up in there. And really, the one dominating axis would be which one? The tiny one or the long one? Which one would dominate? The long one, right? Because in machine learning, what you're looking for is you're looking to distinguish. So the difference between the triangle here and the x is pretty long. Whereas if I look at the distance between this triangle and this x, look, it's pretty tiny. So you see, this one would dominate over this one, this difference. So like this axis would totally dominate over this little one here. And so that's unfair, right? That's unfair to the other feature, which could actually be really important. And that's why you scale it so that you go from this to a totally scaled axis. And you just, again, you just make things in here proportional and things in here proportional. All right, so it's like in one you compress them a little, in the other one you stretch them, but they're all proportional within their scale. And so that's what scaled data is, and it just provides much, much, much better results. Are there any questions about that, guys?
Nope.
All right, good. Good. It sounds like that's clear as well. So that's great. So these are all important concepts, right? So I talked about scale before, and this is really the idea. So once you understand all these elements and you can create your data and create your vector space model and scale it, now you're ready to implement your algorithm. Okay, so now you're ready to implement the algorithm, which is the next thing we're going to do. We're going to imagine we have some data. So now I'm going to go ahead and imagine here I have some data. So something simple, you know, I'm just going to have F1, F2, F3, 3 features. And then I'm going to have S1, S2, all the way to S10, dot, dot, dot. Right? And I have values in here, which when you do your example, I'm going to leave it to you to figure out the data. You can create randomly generated data. That's perfectly fine. But you really want to have some structure to your data because you're doing a classification problem. Right? And then you're going to have some labels. Let's say just a 2-class problem. So 1, 1, 0, 1, 1. Right? So well, maybe, you know, and you'll have more, right? So you want to have a balanced data set, but you have basically 2 classes. There we have 3 1s and 2 zeros. All right? And so then you're going to say, well, for class 1, all the samples in class 1, you know, these 2 features should be high numbers, for instance, right? Whereas for 1s, 0.8, 0.7, 0.81, and this is 0.83, right? So for 1s, they're high values. For zeros, they're going to be low values. So there's going to be 0.20, 0.27, and then for 1 again, it's going to be like 0.65, 0.73, and then for the last 0, it's going to be even lower, 0.15, 0.17. So this is something that I'll let you play with, but if you look as a human, there's a pattern. These here are higher, and they correlate to 1s, whereas the lower ones correlate to 0. That's what machine learning does, okay? Machine learning learns to find differences in patterns, right? So that's the goal of it. Let's see if I can change the pen here. Okay, yeah. So here you can see it wants to learn that there's a pattern there, and then there's a correlation of that pattern with the labels. Okay, that's what it tries to pick up. And the same applies to this. So these correlate with the zeros. Okay? In KNN, however, in KNN, that is even more explicit in the sense that you plot these, the X, right? You plot the X space in a vector space. So I have my vector space there, and now you're going to plot the values, and hopefully we'll be able to see it again. So let me see. All right, so let's try to plot the values now. Switch back to red. Okay, so we have F1, F2, F3, right? And so in the vector space now, I'm going to say, okay, sample 1. It's going to be 0.83 and 0.6. So that's easy enough. Actually, we didn't use F3, right? So we didn't use F3, so I'm just going to leave that out. So actually then, to make this simpler for me, let me make it a two-dimensional. Two-dimensional will be easier for me to plot. All right, so it's just going to be F1, F2. Okay, remember, this is critical to understand the algorithm. Okay, this is what we want to understand here is the algorithm for KNN. So I'm going to plot 5 samples. I'm going to plot the first one, S1. All right, if you notice, it's easy. 0.83, it's somewhere around here. Let me change color again. All right, so S1 is 0.83, and actually, S1, S2, S3, S4, S5. And you can barely see it, but all right. So now we're going to plot S1. So that's 0.83, 0.6. Comes to about here, let's say, S1. Then I'm going to plot S2. That's 0.81, also around there, to 0.7. So that's roughly like there, let's say. So that's S2. Now that corresponds to label 1. Now I'm going to do the S3. S3 has a label 0. So I'm going to change colors for that to something else. Now I look at those numbers. They're 0.20 and 0.27. Let's say about there. That's S3. That's basically being determined by the labels that I have, okay? By the labels that I have. Then I'm going to do S4. That one, again, is green because it's a one label. So the value there is 0.65 to 0.73. So roughly, let's say about there. And that's S4. And then the last one, I'm going to switch over again to purple because it is a 0. All right, and the value is 0.15 to 0.17, so roughly about there. S5. Do you see that? That's what KNN does. KNN just simply takes the values and the labels, so the X matrix and the Y labels, right? And it creates this. It creates this vector space. Now the trick is you're going to have a test sample. This is your, if you will, your train set. Now you have a test sample. Let's take another color. Okay. The test sample now, what KNN does, let's say the test sample is there. And actually, let's do a star. So what does KNN do now? KNN needs to calculate the distance between that, calculates the distance between that, calculates the distance between that. It calculates the distance between that, and finally it calculates the distance between that. All straight lines, right? Or, you know, in that vector space. And that gives you then, let's say, D1, D2, D3, D4, D5. So you end up, for that particular sample star, you get D1, D2, D, oh, it's not gonna fit. For that particular sample star, you're gonna get a vector of distances, D5. Those are your distances now that you have. And how do you get these distances? These distances are calculated based on the Euclidean distance. Usually, it's a function. You'll find a function in Python, Euclid, and then you provide 2 points, right? So you're going to provide the points for the star and then the point for the sample. So let's say, you know, star S1, and then you would do that again, star S2, and so on. So you have to do it for every single point. And that's the problem, right? That's the problem. If you have 1,000,000 samples, you have to compare that star to 1,000,000 values. That's how KNN works, basically. Okay, that's the essence of the algorithm. And so you just have to kind of do that, okay? But this is obviously what you need to do in the code when you write your program. And as I said, I'll help you out, but this will be your next homework assignment will be to implement this from scratch, right? So we'll take some time with it, but that's the goal. So once you compare the star to all the samples, you end up with this vector. So this vector, again, will have a dimensionality of size what? 1, or it's going to be the size of the number of samples, so it's m by 1, okay? M by 1. Does it make sense so far? Are there any questions?
Makes sense.
Okay. So once we have the distances, that vector of distances, the next step is they're kind of all, you know, you just compared it to all the samples. You really don't know which samples are closest, which ones are further away. So what you do then is the distance allows you to determine what are the samples that are closest to your test. What training samples are closest to your test sample? So the next step would be to sort. All right. So now you're going to sort this. So you're going to sort those values in ascending order so that you can bring to the top the shortest distances. Okay. And that's basically the last step. Once you bring up the shortest distances, then you will know, okay, I brought, so for this example, for instance, if you look at these, right? And I ask you, let's look at this graph here. Would you say that the star is green or purple? Most likely. Is it most likely to be green or is it most likely to be purple?
Green.
Green, right? Exactly, because intuitively, you just know, just by looking at these are shorter distances. These are further away. And so therefore, I pick the top 3, and then I pick those distances, and then I just have to look up, okay, for this distance, I took this star and I compared it to this sample. What was the label associated with that sample? Oh, it was a green. Okay, I got 1 green. Then I compare it to the next one. Okay, this is the next shortest distance between the star and the next sample. I look up that sample's label. What is it? Oh, it's green. Oh, okay. And then because I said k equal 3, right? So if I say k equal 3, you know, because it's KNN, you know, k is equal 3, then I look still at a third one, and the third one, okay, the next shortest distance Okay, is this one, I look it up, oh, by the way, the associated label to this one is also 3. Okay, and sorry, it's also green. And there I have 3, all 3 are green and great. When you have, for a binary problem, if you were only using even numbers, let's say you pick 4, the problem is you could have 2 green and 2 purple, and then how do you break the tie, right? So you have to really, that's why you usually go with, you know, uneven number. That's basically the idea. All right, so this is summarized, as you can see, this is summarized in the following description here. The KNN algorithm converts data to vector space model, right? That's the first thing. Then you calculate the distance between your X test sample and all other points or samples, basically, right? Once you have those distances, then you're going to perform a sort. So you sort the distance in ascending order, okay? And then once you have them, then you can pick 5 or 3, whatever it is, the 5 or 3 closest samples and pick the majority class. Okay, so that's basically the idea. Okay, and that's really the algorithm. All right, so this will be the first algorithm that we will have to implement from scratch. As I said before, we're not going to implement all algorithms, but certainly KNN is one that I want you to implement from scratch so that you get the intuition for it. All right, let's see. Sorry, the slides got. Let me restart this. Okay. All right, and so that kind of then summarizes the algorithm there. Okay, so you convert the data to the vector space model, you calculate the distance between your X test sample and all points, sort. You need to pick a distance metric, right? So something that maybe I didn't mention here is that somewhere in here before, when you calculate the distance, right? When you calculate the distance, you need to pick what is called a distance metric, right? And a distance metric can be, there are several ones, all right, that you will look up. I strongly recommend that you actually use the equations instead of just using like a function in Python. However, either way is fine. Initially, you probably want to use a function because it might be easier. But then after that, you would probably want to take a look at the equation just to get a feel for it. There's another one called the Manhattan distance. And there's several ones, right? So, and they all work, they all have some advantages, disadvantages. So depending on your problem, one or the other could be very helpful, okay? All right, so that's basically the summary of the algorithm. Okay, so now let's go ahead. So the summary of this topic is basically that KNN is a traditional machine learning algorithm. It's very easy to implement. We need to define the vector space model and how to represent packets with this model. Okay, and then for the problem of intrusion detection, and then we have learned the mechanism for KNN, for the KNN algorithm. All right, so now let's go back here. What about if you had a multi-class problem? And what I mean by a multi-class problem is that you have, right? You have 3 classes now, or 5 classes, or whatever, S1, S2, all the way to Sn, and this is the features F1, F2, Fm. So here, Does that change anything, do you think, of the algorithm? What do you guys think? The fact that we now have, in KNN in particular, the fact that we have more than 2 classes, would that change anything?
I mean, it shouldn't, right?
Exactly. Because really all you're doing is whenever you find a distance between 2 points, you look up the label. And so you're really just, when you're writing your algorithm, you know, what I'm saying is I want you to make it general, right? Make your algorithm general so that you have a list possibly, right? So, you know, I found class 1 or I found class 2 or counter or something like that. And you just say, you know, you might identify how many classes you have initially, but it should not change anything in the algorithm at all. All right. And that's basically the idea. So now that we're done with this, we can start then to think about how to write this KNN program. Okay. So the first thing is, let's kind of think of this KNN pseudocode. Okay, KNN pseudocode, so that you guys can start working on this. Let's see. So you're going to implement this in, I'm assuming all of you have Python, correct? For this example, you can install, have we talked about Anaconda, guys, in this class? Did we talk about it?
Not in this class.
No, right? Okay. All right. So one thing I recommend is, I assume you guys are using a Windows computer. So if you're using a Windows computer, it might be a good idea for you to install Anaconda, right? So let me go to the website. I believe I have updated this in the website. So you should be seeing the website now for the course. And yeah, so here, this link that says Anaconda, you can click on it, excuse me, and you will be able to just follow these instructions here. You'll be able to download the software, okay? And you can it's a whole package that installs on Windows. It'll have Jupyter Notebooks. It'll have all the libraries that you need. All right, so you can take definitely read through it. You know, it's basically Anaconda is your data science toolkit. It's free. There's over 20 million users worldwide. It's open source individual edition. Is the easiest way to perform Python, R, data science, and machine learning on a single machine. Developed for solo practitioners is the toolkit that equips you to work with thousands of open source packages and libraries. So the way that it'll work, once you install this, is you're going to have at least 2 things where you might work. You'll have you can open a Jupyter Notebook and just start coding in there in the Jupyter Notebook, or you can actually open what is called the terminal. There's a little terminal as well, and in that terminal, you can, it's like Linux. You can type commands and you can run scripts. You can write Python scripts and run them. So definitely, this would be a good resource to start doing this assignment, okay? So read through the package. It is very powerful and complete, and we will be using it for part of the class this semester. It's got all these tools, as you can see, which are a lot of the tools that are used professionally in machine learning. Okay. So definitely, if I guess I forgot to tell you this last week, just install the program. All right. There should be if you're a Mac user, there's going to be a Mac version. If you're on a Linux user, there's going to be a Linux version. And if you're a Windows user, there's going to be your Windows user. I have it installed on my Windows machine, this one basically that I use for teaching. So at some point, we can do some exercises with this. Okay. Additionally, if I go back to the website here, I think you guys are seeing. Okay, so let me, there we go. Additionally, in the link where I said Introduction to Python course, if you click on that link, I know I have a video where I actually show how to use here, Jupyter Notebook. So if you click on this link in this video, it'll show you basically, I know that in that video I showed how to use the software. So this, let me just pause this, let me mute it. But I know somewhere in here, I believe I introduced it. Yeah, towards the end, you can see there, I go over basically some of the instructions on how to get started with Anaconda, Jupyter Notebooks. So you can take a look at that video. Otherwise, you can just, also do that on, find YouTube videos. So it should be pretty straightforward. However you want to do your pipeline, right? I assume you guys are comfortable with Python. Is correct, guys? Is there anyone that is not so comfortable with Python? Okay, all right. So it seems like you're all. So yeah, so that would be the plan. I think that's the best resource for doing that. At least in the beginning of the semester, just Anaconda on either your Windows, Mac, or Linux would probably be the best approach. I've also requested Scholar. Scholar is the cloud of Purdue, and we can do a lot of things with Scholar. I'm hopefully going to have that set up soon. So my goal is that you don't have to do anything in this class with VMs, okay? So we're either going to be using Scholar or we're going to use Anaconda, but that's really the plan. Okay? So now that we've talked about, so now I've talked about the environment, which is what I wanted to make sure I talked about today. And now we can go back then to the code. Yeah. All right, so now that you know about Anaconda, install it, please. It'll have, the great thing about it, it'll have like Python 3.5 or above. It'll have all the libraries, but it'll also have all the simple Python things that you need from scratch. Right, and so then you can start writing your own scripts. You can start writing your own scripts, and the first one that you should try to write is this one of KNN. Okay, so you're going to try to implement KNN. So what are the steps that you need to do? First, create a data set. Okay, now I recommend that you don't read things from files per se right now, although you can if you want. Either way, it should work. But really what you should try to do is try to create the data set and create an X and a Y matrix, right? Make sure that the X matrix has, dimensions m by n, and this one will be m by 1, right? You need to assign labels. So just make it a 2-class problem, right? So, 0, 0, 1, 1. So 2 classes, right? You can define, however, not too many features, F1, maybe the F4, something like that. Create just, a dummy data set. And so you need to start exploring how to do that, okay? There are various ways. And, you know, I want to see what you do before I actually tell you sort of what to do. So today we're going to work on this, but also today is kind of a lab, so I'll let you guys work on this for a little while, and then on Tuesday we will pick up. You'll sort of show me where you are, and then I can start answering questions and better suggestions. But at the end of this lab of KNN, you should feel happy, right, that you have completed the KNN algorithm. All right, so you'll create the data set. Once you have the data set, you have your X and Y, right? You have your X and Y. Then you're going to pick maybe a small test sample. So now you're going to have actually X train, Y train, right? Which, you know, could have 20 samples, whatever. And then you're going to have X test, right? And then Y test. Okay? X test will just be a smaller subset. Maybe you have like 10 samples in it. Okay? And so now what you're going to do is the next step is you have to take each of the 10 test samples and compare them to all the training samples. Okay, you have to compare them to all the training samples, and you have to basically take each point and calculate a distance metric. All right, so this is where start with the Euclidean distance. Okay, so now you're going to calculate, right? Assuming we have, let's give this some dimensions. So let's say this is 100 by 4. So this would be 100 by 1. Then this one, what we're going to say is 10 by 4, and then this 10 by 1. Okay, so now we've provided some distance, some dimensions for X and Y. Then you're going to proceed to identify the Euclidean distance. Then maybe you can figure out, maybe right now you'll start with a for loop, right? So you'll do a for loop, you grab each of the 10 samples and you compare it. So you have to, so it's literally, although for loops, later on you will see that we can do this without for loops by performing other kinds of operations with a library called NumPy. Here though, a for loop might be a little bit more intuitive. So you're going to do for I in range 10, right? And then for j, sorry, in range, what is it? 100, right? 100. And then what do you do now? You know, it's like Euclidean, no, you're going to say d of ij, right? D of ij is going to be equal to what? To the Euclidean, right? The Euclidean of, and this is just doesn't fit here. So it's going to be equal to the Euclidean of what? Of x train, right? X train j. So you're going to take the distance between that and your test sample, which will be x test, x test I, right? No, oh, sorry, I. Do you guys see that? That's basically, although it didn't fit quite as I wanted it in there. That's the main heart of this, right? You're comparing each test sample, each of the 10 test samples to every single one of the 100 trained samples, right? And that's what the I keeps track of the test samples, J keeps track of the training samples. Dij could be some kind of a matrix or some kind of a list or some kind of a dictionary. You'll have to think of the appropriate, a list, maybe appropriate data structure. And then you just figure out, you calculate the Euclidean distance. So Euclidean distance, right? Which is some equation that you have to identify, but it's very similar to that Pythagoras theorem, right? So it's derived from that. So basically what that distance does is it takes 2 points and it calculates the distance between them, right? It calculates the distance between them, and then you're going to store those distances. So we store the distances in D, right? So now that once we've completed this, then we take, we basically take D sorted, right? Where we're going to sort D, okay? And then once we've sorted D, we're just going to take the top 5, right? We're going to take the top 5 values in some way. So it's going to be like 7. Now we need D sorted, but we just need, you know, we're going to slice from 1 to 5. So we just get the top 5. And now right there is we know what are the important distances. Now the key problem is that the distances do not keep track of the labels, right? The labels are not here. The labels are just that vector in Y. However, what you do know is that the vectors are aligned. So S2 is that value, right? So you have to, by the indices, you have to keep track of the values. So what might be better is that in these sorted, instead of having distances, you need to have the actual index. So you need to figure out, so that's the last part that I'm going to leave to you guys to think about, is figure out indices for 5 shortest distances. And then once you do that, you've got the indices. You can look up the indices in the labels, and now you can decide for a test sample what the value should be. Does this make sense, guys?
Yeah.
So this is the general view of it. Obviously, some of these steps occur per test sample, not over the whole test sample. So that might make it easier, is that really this desorted would actually be a line here, okay? It would be a line there because, you know, for a test sample, you compare to all 100 training samples, and then out of those 100, you pick the top 5, and then you pick the indices, okay? All right, let's think about this. Let's take a short break, about 3 minutes. Let you guys think about this a second, and then, you know, since today is lab, and then you can ask questions, okay? So go ahead, think about this, try to lay this out, try to get started with the script, and then we'll use the rest of the time just to answer questions. So let's just let me take a short break here, and I'll be back. All right, so do you guys have any questions so far about this problem?
No questions, but could you put the prompt back up, like the information?
Oh, sure. Yeah, sure. You mean this?
Yes, thank you.
So this is just pseudo code, right? It's not, but it captures a lot of the ideas. Have you guys used Jupyter Notebooks before?
No, but I've used Anaconda before.
Okay, but none. Have any of you used Jupyter Notebooks?
No.
No. Okay. So let's do that actually. Let's do. They're very handy. So we can, but also we can use the terminal later with Anaconda. So you'll have to install this, of course. So you'll have to go to that link and install it. So let me start the Jupyter Notebook first. So I need to share this. Okay, so you know. Hold on. So, all right, so it's starting. Okay, so there is. This is a Jupyter Notebook, which is basically a kind of a web-based. You get like on the browser, you get pages. So if you go to desktop, you know, let's just say I'm gonna go into some folder, okay, and I have my Jupyter Notebooks in here, right? So all the Jupyter. So if I want a new one, all I have to do is I click on New. I'm gonna select Python 3, and there you go. That is a Jupyter Notebook. And so they're handy, and we can use them in the class. You can do anything with them, you know, TensorFlow, PyTorch, regular Python, NumPy, etc. Okay, so usually what it does is, you know, you write your Python code in here, you know, like that, hello, right, and then you run it, and then you see the output. But then the information is stored sort of in memory, so you can continue writing other things in your code. You guys see that? Now, if we wanted to import a library, let's say like NumPy, S, and P, right? So this would be the idea. You know, see it basically does it. So basically, this library is available, and now we can use it to implement other things in our code. We can probably even do import TensorFlow as TF. All right, so you know I'm gonna try to run that. Oh, no module TensorFlow. Okay, so maybe I need to install that one then. Let's see, pandas, import pandas as PD. All right, so that one is there. You see that? So I'll have to check and see why TensorFlow. Let's see, PyTorch. Import PyTorch as torch. All right, so it seems like these probably require a little bit more. All right, so I'll look. We're not going to use TensorFlow or PyTorch right now, but certainly NumPy and pandas are libraries that you're going to come across as you're doing your work. You can, if you want to reset, like clear everything and reset it, usually I just do restart and clear output, and then hit on that. And see, it goes back to just the code. And then when you want to execute something, you click on it, and then you hit run. Make sense?
Yep.
And it's pretty simple, really. For the terminal, you have to go to. For the terminal, you have to go to Anaconda, and it's, I think, Anaconda prompt. So click on prompt, and then if I share this, it'll be basically like this. You can see it saying this is the base install. So then we can try to install environments. And you can see now it is basically giving me some environments. But the great thing about Anaconda is that you can actually create environments, and you can say what you want in that environment. So I could say, for instance, Conda create, and I give it a name like TensorFlow 3. And then I can tell it which versions of programs I want installed. And then that way, whenever I want an environment, I can just reference it by calling it by name. Okay, then you say something like conda activate so and so. So we really don't need to get into that right now because, as I said, we're not using any complex libraries like TensorFlow or PyTorch. But later on, I will show you a little bit more about this. But you can easily figure it out as well. So these are the two environments that we can use. The advantage of this, of course, is that we can run scripts, right? So we could do Python, myscript.py, and then that would be the same idea. We run that program of code that we have written. Or we can just use, for quick prototyping, the Jupyter Notebook is also pretty simple. So I would actually recommend, since you guys haven't practiced, haven't used Jupyter Notebooks yet, that you actually try to implement this homework in the Jupyter Notebook. That way it'll get you a little bit of exposure to it, and but you can do it in both ways, really. Questions? Make sense?
Makes sense.
Okay. Yeah, so that's really what I would recommend, okay? So first thing first, we're not going to get into Scholar yet, but just install Anaconda. I've shown you the two interfaces that we can use in the course, Jupyter Notebooks or this prompt over here. I've only shown it on Windows, but if you have a Mac, you're a Mac user, or Linux, you can, basically it works exactly the same. Just install the version appropriate to your operating system. And then after that, just start working on implementing the KNN algorithm, okay? Now, what I would like to see is that you make some progress. So on Tuesday, when we meet again, since we have a homework, right? We have a homework that's due by Sunday. So work on that homework, try to complete it, and have it submitted by Sunday. If you do that, I'll try to read the homeworks, and then by Tuesday, we'll have a discussion about that homework, and then also try to work on this algorithm. Now, this one's not due, obviously, yet, but just try to make a little bit of progress. We'll discuss it on Tuesday, and then once we discuss it on Tuesday, we can see how to get it solved. Okay, but as I said, my goal is that this whole thing we should be able to do, even calculate one of the metrics, accuracy. We're all going to do everything from scratch, right, by hand. Maybe with the help of NumPy, but otherwise, we're going to do everything for this algorithm, and hopefully this will give you really good intuition going forward. Now, we're not going to do this for every single algorithm, but we'll do this for 2 or 3, okay? All right, so any other questions?
Not from here.
No questions.
Questions? Everyone understand the homework assignment and everything?
Yep.
Okay, great. All right, so I don't have anything, any new content, right? We still have 2 minutes, so I'll pause the video, right? Because I don't have any new content.